Hi everyone, I'm Livia, the M31 Foundation IP Development Senior Engineer. Today I'm glad to introduce M31's memory and standard cell in T22 UL process node. Let's begin. In an SoC chip design, Foundation IP plays an important role in chip performance. There are two important elements, memory and standard cell. Memory is like a human brain in electronic products. Electronic products should implement memories as they are used to store information and extract data to run different applications. For the reason, it's a very important part in 3C products. What about standard cells? Standard cells are like living cells in electro products. Circuit designers can compose them to make any functions in any way they want in ASIC design. For M31's memory and the standard cells IPs, there are three key points need to be designed upon customers' request. The first one is power, including AC and DC power consumption. The second one is performance, which is the operating frequency of the IP. The third is area. I will introduce memory part first, and then the standard cell. For the above three design key points, M31 shows the 22nm memory platform in the table. If you want your products to operate at low voltage or not charge often, select the ULL, Ultra Low Leakage compiler, which always used in variable IoT devices. There are 5 types of UL-based cell memory compilers: single pole, one pole, two pole, pseudo two pole, and ROM. Moreover, if you want your products to save area and operate with high speed, select the GL, General Compiler, which is used in plug-in devices usually. There are 3 types GL-based cell memory compilers: one pole, two pole, and L1 cache. Particularly for the L1 cache memory, it is applied on the CPU application, and its spatial fast data access time design will boost up the performance of the chip. Regarding the 22nm memory platform features, we allow chip designers could have different power domains and consider performance and power, including dual rate design, which can use wider range of voltage. Peripheral power is available in a low power range from 0.5 volt to 1.05 volt, whereas array power is available in a low power range from 0.72 volt to 1.05 volts. By the way, our memory operation modes are very flexible with 3 power modes: standby, retention, like computers in sleep mode, and power shutdown. As you can see in the chart, during the retention modes, you can set up to 75% power in your chip design and up to 95% in the power shutdown mode. M31 supports DVFS, dynamic voltage frequency scaling, function in a 22nm memory platform. There are 2 operating modes with different power and frequency in the product. One is the turbo mode that operates at the high voltage frequency, and the other is the normal mode that operates at low voltage frequency. In traditional DVFS operation, the system needs to wait for a period of stabilization time over 10 cycles to change the voltage frequency before it sends out a signal to memory. However, with M31 memory DVFS operation, it takes no time to immediately switches the DVS pin, unlike the traditional DVFS operation, which requires waiting for more than 10 cycles. In addition, M31 adopts 2 skills in the UL compiler for both dynamic and static low-power designs. One is separating the BIOS voltage from the internal power of the memory to reduce the leakage rate by about 10%. The other scheme is that we allow memory operating at lower VDD to achieve dynamic power saving. We have the RA, read assist, and the WA, write assist, circuit that enable memory to operate at the low voltage of 0.72 volts. As you can see in this figure, without the RA and WA circuits, the UL compiler can only operate at 0.93 volts.